So here's a demonstration of Young's double slit experiment, and what I'll try to do here is show you how the nodes and antinodes appear. Remember that nodes are areas of destructive interference, where a wave crest from one source would meet with a wave trough from another. The trough and the crest would interfere with each other in a negative way or a destructive way, resulting in a node or a flat spot. If we were doing this in water, it would be a flat spot on the water. An antinode is an area of constructive interference where a wave crest from one source meets a wave crest from the other. They interfere constructively. Now, what we have here on the left is we have one source of a wave. You can see that there's a crest just leaving the source, and over on the right hand side we have another crest just leaving. We put these two sources 30 centimeters apart to show that if they're a large distance apart, there's not as much interference as if they're close. But we'll start with them far apart. Now the wavelengths are 20 centimeters apart, which means that, of course, that these two wave crests, a crest from the left and a crest from the right, are the next crest is going to be 20 centimeters behind. So if we just take a look at this and watch them as they move outward, you can see that when they meet right in the middle, right at this point right here, you can see that the crest from one meets a crest from another. And as you can see at the bottom, it says constructive interference is occurring, and you have a maximal amplitude. And of course, they also state that the path difference between the left source and the right source is 0 wavelengths. That means there's one wavelength. Actually, there's because the wavelength is 20, you've got actually not quite a full wavelength, but you've got a crest meeting a crest. So the distance between the source and the wave is the same from one source as it is from the other. And we get what is called a maximum at that point, where a crest meets a crest. If we move over a little bit further to the right here, now notice that from this particular point, there's a half a wavelength difference. And when you have a half wavelength difference, you get destructive interference or minimal amplitude. This would be where we have a crest from one meeting a trough from the other. And you'll see that these red lines represent areas where you'll see wave crests, and these darker lines would represent areas where you would see an area of destructive interference. For example, right at this point right here, what we have is we have a wave crest from the right side meeting a wave trough from the left side, and therefore we get destructive interference. Anywhere along this line, we get destructive interference. Anywhere along these red lines, we will get constructive interference. Let's just take a look and watch for a second. And you can see that at this point right here, we are getting a wave crest meeting a wave crest from one. Notice though that there are different numbers of crests. Here we've just got a short distance from the right. Here we have a long distance from the left. They're actually saying that there is exactly one wavelength difference. Now let's change the parameters and make the wavelengths a little bit smaller. If we make the wavelengths 10 centimeters, then we see a much different pattern, although it still has nodes and antinodes. Here are the antinodal lines, and here are the nodal lines here. So we have antinode, node, antinode, node, and so on. And notice that along these antinodes, we'll just pause it somewhere. And notice right here, we've got, again, 1, 2 wavelengths from the left, and about 2 wavelengths from the right. Actually, I'll just get it going so that it's just starting a wave. There we go. And at this point up here, we have just a wavelength starting. So we have 1 wavelength, 2 wavelengths from the left, and from the right hand side we have 1 wavelength, 2 wavelengths. If we move over to the next antinode, which is let's see, that would be let's say right here, then we have 1 wavelength from the left, and we have from the right we have 1 wavelength and then 2 wavelengths. Notice the path difference is still a full number of wavelengths. And you can change the patterns as much as you like. We could change the wavelength, make the wavelength much smaller, make it 5, and then notice we just have more and more areas of constructive and destructive interference. This goes along with Young's double slit equation. Lambda is equal to xd over NL. If you solve this for x, which is the distance between antinodes, notice that since x is equal to NL lambda over d, as we make the wavelength shorter, the value of x also becomes shorter. So if we change this wavelength to 1, the wavelength is getting much smaller, therefore the distance between the nodes and antinodes will get much smaller. And so we start to get quite an interesting pattern there. If we made the wavelength very big, let's make it back up to 20, then notice that there are very few. The distance between antinodes and nodes, or sorry, the distance between one antinode and the next is very, very large because the wavelength is getting larger. As we make the wavelength bigger, the distance between antinodes also gets bigger.